All right, everyone, here we go with the notes for Chapter 3, Audio and Video Technology. This chapter is going to be done over 3 videos. This first video is going to cover sections 1 and 2 of your notes. The basic principles of media technology. We're going to go through some of the different elements that go into the equipment that you use on a regular basis. First, talking about facsimile technology. A facsimile is something that creates sounds from a speaker, pictures from a TV screen, anything that is a mere representation of its original form. Usually when we think of facsimile these days, we tend to think of a fax machine where you send documents from one place to another. The same principle applies. When you receive a fax, you are receiving a representation of the original document that was fed into the sender's fax machine. Same thing here. When you're hearing sounds coming out of a speaker, you're hearing a representation of an original sound that was recorded into some sort of device or put into a microphone and transmitted through radio waves. Same thing with a television. A camera picks up an original view of something real life and sends that across waveforms to your TV screen, and it creates a picture. Fidelity is a measure of how faithful a reproduction or facsimile is to the original. Most of the time when you hear the word fidelity just in normal culture, you think of fidelity in terms of perhaps if someone has committed infidelity, like if somebody has cheated on his or her spouse. What we're talking about with fidelity as opposed to infidelity is staying true and staying faithful to the original intent of the communication. Much in the same way that a marriage partner that is committing fidelity, not infidelity, but fidelity, is staying true and faithful to the marriage. So, where you get a sense of where these words come from. If we're talking about high fidelity, we're talking about audio that is close approximations of the original speech or music that it represents. Much of the technical development of radio and television has been a search for better fidelity relative to the device and to the needs of the consumer. So there's all sorts of different ways that we can look at that in terms of how quality the audio is, how crisp and clean and clear video is. So the higher the fidelity, the more true that it represents the original, the more true that it represents life around us. Signal loss is the loss of fidelity in the process of transporting a sound or an image. Another term for this would be degradation. So anytime that we are trying to duplicate or simulate some original piece, sometimes some of the information gets lost in transmission or gets lost in the saving process. So you do have a bit of that signal loss or degradation going on in that process. Transduction is the process of changing one form of energy into another. If you look in your textbook, there's a great example of how many different transductions happen in the process of mass communication. I would encourage you to take a look at that to kind of follow the path of how that works. And it's not just going from one form of energy to another. There's a lot of different transductions that happen, whether you're recording your voice or you're taking a picture or you're filming something on your camera or your smartphone or whatever. There's several different actions that are taking place in order to make that recreation a possibility. And at every phase, at every transduction, a loss of fidelity is possible. What happens is that you may also get some interference, what we call noise, and any interference that is unwanted is considered that noise that would create some sort of a distortion of the sound or a distortion of a picture that's being created. The good, the bad, and the ugly of digital. When an analog recording is made, it becomes complete and has specific parameters that are not easily changed. What happens when you do an analog recording, say if you are recording something to a cassette tape or to an old VHS tape, the way that information gets recorded onto the tape, it's done in such a way that you can't necessarily pick things apart or edit things and manipulate just by moving around a couple of files or pixels or something like that. The piece that is recorded in an analog recording tends to be a unit in and of itself. As digital technology, though, becomes more prevalent, producers found that it was easier to scale the message created for different devices. And what we mean by scale here is that we can record audio at different bit rates, in different file sizes. Same thing with video. We can show different types of resolution, how many dots per inch we look at a video image, how many lines that we see of a video image, and all of that is a difference in shape or a difference in fidelity. Compression is the idea of making larger video and audio files smaller in size, impacting speed and shape and fidelity. So it's possible rather to be able to get an entire scope of a piece of audio or a piece of video into a file that is much smaller in size, smaller in kilobytes and megabytes, gigabytes, in order to make it easier to transport and transfer and all that sort of thing. But the more that you compress that file and try to fit large stuff into a small area, you're going to wind up leaving pieces behind. Digital media is easier to copy, distribute, and alter from its original form, and that also includes being able to do so illegally. Ever since digital transfer of media has been possible, it's become quite a thing for people that own content to try to protect that content. And there's been different protocols that have been put into place to help copyright holders protect their creations. But it always seems like someone knows how to work around that. And if they really want to steal something, they can do it. It becomes an ongoing situation for creators to be able to protect their work and to try to keep the rights of it and earn the income that they are rightfully able to earn for what they have done. Oscillation and the waveform. Oscillation is the vibration of a sound or radio wave. One way that you can look at that is that because sound and radio waves are actually physical elements, even though we don't see them, what happens is when a wave goes through the air, it actually pushes through the air and it causes the air around the wave. As the waveform is pushing through, it is displacing that air and causes vibrations. The waveform, by the way, the footprint or image of an oscillation. The way that you can look at this is think about whenever you throw a rock into a pond or a lake and the way that you see the ripples of the water move out from the point that you threw the rock into the water. It's a similar sort of way to how waveforms work in terms of how the rock displaces the water. That's how waveforms displace the air in order for that sound to travel. Frequency and amplitude. Frequency is the number of waves that pass a given point in a given time. This is measured in cycles per second, or the notation that we use is hertz. So the number of times the completion of a cycle happens within a second of time, that is the frequency of a wave. The wavelength is the distance between two corresponding points on a wave. For example, if a wave starts at a 0 point, then goes up, then goes back down, crosses 0, continues going down, and then comes back up to 0, that is a wavelength. Amplitude is a wave's height or depth from its normal position or its position at 0. So how tall the waveform gets and how far down below 0 it goes, that is the amplitude of a wave. Frequency response and bandwidth. When we're talking about frequency response, we're talking about the range of frequencies that a device is capable of receiving. One way to look at this is if you study the frequency response of a microphone, for example. You'll be able to see the lowest frequency that a microphone is able to pick up and the highest frequency that a microphone is able to pick up. And the better that a frequency response is, the greater the range that you can see of the low point and the high point, the greater the fidelity of the device is going to be. Because if it can pick up sounds that are extremely low and sounds that are extremely high, then you're going to have greater fidelity. It's going to be a much more true representation of the original sound. AM sounds somewhat tinny compared with FM because AM has a much smaller bandwidth than FM does. And as a result, AM cannot reproduce all of the frequencies the human ear is capable of hearing. So if you've ever scrolled across the AM dial and wondered why it sounds kind of crackly and AM tends to not broadcast in stereo, it's because the bandwidth prohibits it from being able to have a much more full, true sound. Digital television allows the broadcaster to be able to decide how much bandwidth to use for various telecasts. And the way that we can see that is if you have regular television, broadcast TV that you don't subscribe to cable or satellite, and if you're going up and down the channels, every channel, for the most part, is going to have several different sub-channels within it. So you've got channel 17 that broadcasts out of Raleigh. You can pick up 17.1, 17.2, 17.3, and each of those dots is taking up a certain percentage of the bandwidth that is available to channel 17. So you may find that some subchannels of some television stations are able to broadcast at a higher quality on certain subchannels, and they may broadcast at a lower quality on some of the other subchannels. Now, as far as channel assignment goes, the FCC determines a station's bandwidth when it determines its frequency. So that is something that is set by the government that TV and radio stations have to live with and abide by. Let's start talking now about some of the steps in the media distribution process. All right, let's first look at signal generation and recording. Let's look at it from the mechanical aspect. So the mechanical means of recording and creating signals are used to translate sound waves into a physical form. That's what we consider analog technology. So when you speak into a microphone, the microphone is physically picking up that sound wave, because again, sound is a actual physical thing because it displaces the air, it moves air around, therefore sound has the ability to displace things around it as it travels through. That includes in the microphone. There's parts of the microphone that move whenever it detects sound coming at it, and that's how it picks up a recording. Digital audio was made possible by the development of the means of a signal generation known as pulse code modulation, or PCM. If you want to take a look at some of the different waveforms out there, some examples of that, you can take a look in your textbook and it will give you a pretty good representation. Digital recording technology. Once a sound has been transduced into an electrical current, it can be sent then to a device that converts that signal into a series of samples that represent both the frequencies of the sound and its loudness or its amplitude, how tall, how deep it moves from zero. So then after that signal is converted into those samples, we have what happens that's called quantization. Quantization is the process of storing and coding digital information. The higher the sampling rate, the higher the quality of the audio file. And you'll talk more about this in your radio production class, but in terms of what we consider to be broadcast quality audio, it's going to be this number right here, 44,100 hertz. It's what we call the Nyquist rate, and it's basically what has been determined to be the frequency at which we can understand audio and hear it fairly true to life. That's the closest number that we can get to representing true natural audio. CDs and DVDs, a laser beam sees the pits engraved on a CD or DVD to detect its information. That's how you're able to transfer the items that are on your disc through your player and then on out to your speakers or to your television set. A little bit more about DVDs, digital versatile discs. They're capable of reproducing multiple channels of audio. As far as the storage mechanism, DVDs, HD television, they use the MPEG-2 format, and MPEG-2 will compress the large amounts of data that is needed to store the information for the video that is on the DVD or being broadcast by your HD television. Let's talk about audio formats. The two main ones that are out there are MP3 and WAV. MP3s use recording compression technology. It was developed for file sharing and exchanges of files on the internet. It was trying to bring all of the information of the audio in such a way that it can fairly easily and quickly be transferred over networks. MP3s are popular for music players and storage on CDRs. MP3s come in a variety of bit rates that affect playback quality standards. So you can change the hertz rate, you can change the number of bits that are involved in a piece of audio. Whether it's stereo or mono is also going to affect the size of a piece of audio. So MP3s can be rather small or they can be rather large depending on how much information is packed into the data of the MP3. WAV files and some other formats that are out there do not compress audio. It's what we call lossless audio. So when you get a WAV file, most WAV files are rather large because it contains all the information on that audio that it possibly can. Alright, so video signal generation. Video generation uses a concept called scanning. Scanning is a visual equivalent of audio scanning in that the camera scans each element of a picture that you see on your TV line by line by line. The ways that television had traditionally done this is by a concept called interlace scanning. So in the United States, television screens were showing pictures with 525 lines of information from the top to the bottom of your screen. But the way it would create the picture was that as it was going through and creating its 30 frames per second, you would see, if you were to slow down everything so that you could actually see this happen, you would see from top to bottom, you would see the first line of the picture being drawn. Then it would skip the second line and draw the third line. It would skip the fourth line and draw the fifth line, on down and down and down until it got to line number 525. Then it would go back to the top and it would fill in the other lines, line 2, line 4, line 6. And it would repeat that process in order to bring you a picture. Retracing was the process of replicating the scan to produce the image on the television screen. Standardization, NTSC, that is the format that we used in the United States. Again, 525 lines at 30 frames per second. PAL was the European standard that showed 625 lines of content on a screen at a time at 25 frames per second. So there are two different ways of being able to show content on a screen. Bandwidth is the amount of space a radio or television channel occupies on the electromagnetic spectrum. The greater the bandwidth, the greater the fidelity or the capacity. So if you have a lot of bandwidth available to you, you're able to put a lot of information in there, and you can either break things up so that you can have several streams of content, or you could use that whole bandwidth to be able to create the crispest and clearest audio and video being sent out over the airwaves. TV stations in the United States have 6 megahertz of bandwidth allotted to its individual channels. Let's talk now about digital television and high-definition TV. Ever since the transition to all digital broadcasting happened in 2009, we've gone away from that old 525-line analog transmission, and now we have content that is scalable from anywhere from 480 lines on your TV screen to 1080 lines, and we're now starting to get into 4K as well, which would be 2160 lines. Television can be shown in full screen, which is a 4:3 aspect ratio, what we call letterbox television, or widescreen, which is a 16:9 aspect ratio. More information on your textbook on this. Lines can be interlaced or shown line by line, and if it's shown line by line as opposed to interlacing where you're showing every other line then going back and filling in the gaps, line by line straight on down would be called progressive scan. That's where, by the way, you get to see distinctions whether something was recorded in 1080i or 1080p, interlaced versus progressive. The ability to show programming in different qualities makes it possible for broadcast TV stations to carry additional programming on its channel allotments. As we said, television stations in the United States on its channel allotment has 6 megahertz of bandwidth. So it could use all 6 megahertz to broadcast one stream of content, or it could break it up to say maybe give 4 megahertz to one particular stream of content, usually their .1 channel, for example, and then use the other 2 megahertz for another stream of content, or break it up in many different ways. I've heard of TV stations doing as many as 8 different streams of content on its channel. Modern TVs can scan images at 120 frames per second, creating the possibility to transmit separate left and right eye pictures, in other words, 3D. Haven't seen a ton of this out there yet, but it definitely is a possibility. Let's take a look now inside the camera. And again, your textbook can help you with a diagram that is there. You've got an object that is out in the real world. It is captured by the lens of the camera by means of light showing into the lens. And then that light is being put into a filter by means of a prism inside the camera. Then within the camera you have a filter of the different lights that are being brought in, images of red, blue, and green. Each color has its own light-sensitive wafer called a charge-coupled device, or a CCD, and it creates images similar to how a printing press does with each color, and that creates rows of dots that we call pixels. Very much like pixels that print out if you have a inkjet printer for your computer. So the end result of what the camera is able to record, what we see is basically a combination of red, green, and blue lights. And then we also see the addition of black lines, and this is known as blanking pulses that kind of help fill in some of those gaps from what the camera picks up. A synchronization pulse is what enables the output of two or more cameras and other video sources to be mixed together by a camera control unit or a switcher. So it's basically kind of a marking point whenever you have more than one device that is being used to put together content, and that way everything stays in sync with each other. Composite video signals the complete TV picture for NTSC television. That is combinations of red, green, blue, and black. Component video is the separate output of color signals used by digital TVs and DVDs, providing better picture quality. So the composite video would be kind of more that analog style of showing pictures, while component has a better picture quality by being digital. Okay, let's talk now about audio amplification. An amplifier is a device that boosts an electrical signal by using an external power source. Those of you that play musical instruments, guitars for example, you may hook your guitar up to a soundboard using a 1/4-inch cable, but on the way to the soundboard you might have something called a direct box, and the direct box allows you to first off transfer your 1/4-inch connection from your guitar to an XLR connection that your soundboard uses, but the direct box will also amplify the signal. It'll make that signal stronger, and many times there's going to be an extra power support, an extra power supply that is going to help to make that happen. Some of the functions of amplification: it increases power, it increases output, it also modifies the audio. You can do different things to help change the shape and scope of a sound, things like adding bass or distortion, and that process is called signal processing. Mixing consoles, control boards, computer programs all help to shape the sound that is coming through towards the final product. They provide the ability to mix and combine signals, and they contain amplifiers and special circuitry to help create that right mix of the sound. Desktop audio, amplification, and mixing are now possible on PCs. As you learn to use audio editing software, you'll get to see in great detail how that comes to be. Let's talk now about video amplification and processing. In most TV programs, the camera and other video input sources are mixed together before they are transmitted by use of a switcher to select what elements or element is desired at a certain point and time. So just as you can kind of mix sound on an audio board, there's ways to mix what cameras are being used and what other things are being picked up by cameras for the purpose of creating television content or video content. Transitions from one source to another include the cut, which is an instantaneous switch from one picture to another, and the fader, which allows a director to dissolve from one image to another or to fade to or from a black screen going to the content. Keying allows for a split screen for two or more cameras to be shown at the same time. And then the chroma key allows for use of a blue screen or a green screen background to have videos or graphics be keyed in to a camera shot. The best example of this would be when you're watching your local news and a lot of the weather forecasters may be standing in front of one of these blue screens or green screens so that the graphics of the weather map are able to show up behind him or her. Digital video effects allow for various on-screen displays such as freeze frames, shrink and enlarge, and positioning. And there's all sorts of different types of software that you can use to make these things happen. And there's a small sample of some of the software that's available. OBS, Open Broadcast Studio, is one that you can actually download and use for free. All right, this is a good point to take a break, and we got much more to cover. We will continue on with these notes when you join me for part B of Chapter 3.